Well, thank you very much for the kind introduction. And I should add the very kind invitation. You'll forgive me, I hope, that I sit. It's hard for me to stand up for any length of time. Stopping here for a moment at the first slide, I want to tell you that when I made out that slide, it wasn't much work, but I was really bothered by the fact that I'm going to be there standing or sitting before an audience, and I don't know how to pronounce the first word on the subsidiary line. So I was hoping that I'd be clued in before I gave my talk, and so now I know that the name of this eminent institution. Oh, okay. Well, that's what you get for having a lot of communication around. So here it is, Imitating Stradivarius, and I want to begin by telling you about the contributors. I guess, of course, I'm a contributor. I wouldn't be speaking here, but I have had a very fruitful partnership with Joseph Curtin. I'll read to you what this says. Gabi is a physicist. He wants to find out how a violin works. If it ends up being useful in making better violins, that's gravy. Joseph is a luthier. He wants to learn to make better violins. If it ends up contributing to basic knowledge, that's gravy. And so that's a very, very fruitful collaboration, since we each have our own names and yet we lean on we each lean on the other. Now, I want to begin with a few words about what is a musical instrument. And facetiously, I write here, why is the frying pan, whose sound you just heard, not generally considered a musical instrument? And lots of points of view have been brought on that, on this topic, and I don't really, I'm neither qualified nor do I have time to review them all. But I was looking for a definition that could be applied transculturally, for example. I didn't want to make things depend on harmonic overtones, which is important for Western music, but not otherwise. But I think in every culture, of the various objects capable of producing sound, a musical instrument is distinguished by the fact that it can be played very well. And now I'm going to try to explain what I mean by that. If it makes essentially only one sound, which is true of a frying pan, although you could push that, but basically there are instruments that can make only one sound. Probably the one in the Western culture that's most like that might be the triangle. I'm sure that the triangle virtuoso would argue with that, but I don't think that the variety is really very great. And a musical instrument is distinguished by the fact that it can make not one sound, but a large variety of sounds, and somebody who studies how to play it gets to the point where he or she can control which of those sounds arise. I quote here the saying that has been said about many outstanding violinists, that he could make a cigar box sound beautiful. Well, I don't know whether that's actually true, but it is true that a good violinist, his training, his technique consists in the variety of sounds that he can bring out of the instrument, and the fact that he can control it very well. So I'll digress here for a little bit and talk for just a few seconds about the piano. I think that comparing, from this point of view, comparing a piano with a violin, it's true that an excellent pianist needs only to play a few notes, the beginning notes of some piece, and you will be astounded and affected, and you'll say, "Oh, isn't that beautiful?" In fact, some people, a sizable number of people, claim that even playing one note, you can tell a great pianist from one who isn't. But I don't want to go into that controversy. Still, the fact is that if your cat walks across the keyboard of your Steinway, you will hear the Steinway. Whereas with a violin, if you have no idea how to play it, you won't even be able to make a sound. So the range between a novice and a virtuoso is, I think, much greater for a violin, and that's what makes it so fascinating. Now, an electric violin, not as many people know about electric violins as know about electric guitars, so I make that comparison. In either case, it's played just like the real instrument, but it's practically inaudible until plugged into an amplifier. The electric signal that electric violin produces communicates simply the force exerted by the strings. That's the only signal that validly comes out. Electric guitars are a little bit different because there are a lot of electric guitars made that have actual controls, knobs that you can turn to adjust the tone and so on, which makes it one step different from an electric violin. An electric violin doesn't have any characteristics at all except the characteristics that are put into it by the bow of the performer. Now, a real violin is, of course, quite different. This is the sound of a real violin in response to a short pulse applied to the bridge. That's the graph on top here. This is a function of time, and the pulse is applied right at the beginning, and this is the thud. That's the best way I know how to describe it if you don't want to get technical. It's a kind of thud. It lasts for some fraction of a second. I mean, a fairly small fraction of the second if you don't have strings that are allowed to vibrate. Otherwise, they can last for a while. And you can convert that to a frequency response by mathematical manipulation, by computer manipulation. So that's a real violin, not an electric violin. Now, this is an electric violin. If you apply an impulse, which you can barely see here, this is the initial impulse. It's sort. Now, how did it get there? Yeah. So an impulse and then the frequency response, which is obtained by the same mathematical operation called the Fourier transform, is going to be flat. That's just a property of an impulse. And so what you have on the bottom graph is a abscissa that runs from 0 to, oh, I don't know, about 10,000, probably not quite 10,000 hertz. It falls off at the end because of uninteresting reasons. But otherwise it's completely flat. And I do want to make a comment about the nice blanket pattern with which it's shaded. There are these vertical lines which are colored. That's a work in progress. That's an attempt to put phase into the same graph because the hue of a color goes around a circle and then starts again, just like the angular and the phase, which is an angle that goes from 0 to 360 degrees. If you associate those two, you should be able to show the phase. This is for the specialists. Otherwise, I won't spend any more time on it. It actually, in this case, doesn't work very well, but I know why. So, because the response of the electric violin is so very simple, we can calculate what it would sound like when we play a familiar piece. And the word empty, which is shown here, means that we're using that kind of frequency response which doesn't have any processing, but just gives the force exerted by the vibrating string. So, well, that's an electric violin. Well, we don't need to listen to the whole passage. But then here is something which is, I think you will agree, different. Okay, so what is this? I'm going to play lots of examples. I won't play the whole passage. It's about a third of the first movement. The third of the first movement, the Adagio movement of Bach's Sonata No. 1 for unaccompanied violin. And I'm sure a lot of you recognize it and know it. It's a beautiful piece. It starts in G minor. It ends up in the dominant D the section that we played, and that's the standard situation. Then comes a kind of development which starts from the dominant D and ends up in the tonic again. That's probably about twice as long as this first section. But let me just show you, there's a red mark here which signifies the place where I will play the other examples too. You'll hear this passage a lot of times, but I'm not going to bore you by playing the whole thing every time. So what I asked, what is this? So this is the first answer. It's a section of the first movement of that sonata. And the answer to number 2 is it was performed by Ilya Kahler, a name which some of you may know. He's I don't need to tell you what a good violinist he is, because you heard that. This is an acknowledgement with admiration and gratitude for having done this. But the real answer that people are looking for is it was performed with the sound of the Guarneri del Gesù Vieux Temps. With the sound of, actually what he was playing was an electric violin, the same as you heard in the first example, but he was playing it with the sound of the vieux temps. And if you don't know, if you're not familiar with vieux temps, it's a very famous violin. It was made by Guarneri de Gesù. That's his nickname, but it was built in 1741. And it's a very famous violin, and it's now in the hands of a Chicago dealer who has offered to sell it for $18 million. Now, of course, it hasn't sold yet. And it's a fair guess that when it gets sold, it'll be somewhat less than that, because he's a very clever dealer and isn't going to tell you what he really expects to make on it. But if it sells for $18 million, that will be the highest price ever paid for any violin. So it's a very famous violin. Now, but when I say it was done, it was played with the sound of the vieux temps, how do we do that? Well, here's how we do it. We get a violin that we want to imitate. We don't have $18 million, so we can't buy it. We borrow it. And then we mount it in this rig. Actually, there are variations of this rig, but that doesn't matter. It's mounted in this apparatus where a tiny hammer is pivoted. Here's the hammer. There's the head of the hammer, and it's pivoted up here. And this thing here is a long exposure cable for a camera, so that the person operating it can stand aside and not get involved with what's going on. Well, what's going on is that this hammer taps the side of the bridge, and the microphone, which you see in front of the violin, picks up the sound of the violin and records it, of course. And that's all we need to know. That takes a few seconds, and including mounting it and setting everything up, it takes a few minutes. But after that, we return the violin to its owner, we get back our $18 million deposit, and after that we can use the sound forever. Now, I have to explain that. Some of you know about this, of course, but I can get a pointer like this. There's a mathematical process that's used starting with a recorded impulse response and an electric violin input. That is, the input which gives you the force exerted on the string. And that can be done anytime. It can be done, you can then play any piece you want to. So you have a flexible input, and you combine it with a known impulse response, and essentially, if you want to get an intuitive notion of this process, which is called convolution, it's a process which mathematically subdivides the actual input into thin slices which are pulse-shaped. I mean, they're automatically pulse-shaped. The pulse is something which has a magnitude for a very short time and then returns to zero. So if you think of any other input as being composed of a string of pulses of varying sizes, and you know the response that each pulse separately has, then you, or probably you should say the computer, can add it all up and get the output that you would have obtained if you really played on that violin. And the frequency response is here. That's on the side. It's invaluable for analysis if we want to talk about the violins and discuss its characteristics. It's very hard to do that from the impulse response because one thud sounds like another thud, unless, you know, maybe a very practiced ear with a lot of training. But there's lots you can see from the frequency response. And, you know, since a very good player can bring tears to your eyes playing on a cigar box, we decided to try the method on a cigar box. So here's the same apparatus. We don't see most of it, but you see the hammer. The hammer is about to hit the cigar box, and there's a microphone nearby, which is not shown, which is going to record the impulse response, and then we process things in the same way. So here's a comparison of the cigar box with the plain vanilla electric violin. By the way, I should add at this point, I should call to your attention that the first example I played, which compared the cigar box with the Vietong, I played both the same example through them both, but I didn't want at that point to comment on the various aspects of the quality. But now I wanted to tell you that one thing about this, the empty violin, one thing about playing a just ordinary vanilla, as I say, electric violin, is that you don't hear vibrato, or you hear it just vestigially. We think of vibrato as a rocking of the finger, which makes the string longer and shorter with some periodicity, you know, typically maybe 5 or 6 times a second. And so there's a frequency modulation. The note actually goes up and down in pitch. And that, of course, you hear. But a very important effect that you get with a real violin, and you get it in spades with a Vietong, is that as the frequency changes, you also have, since you have a very uneven frequency response, you're always traveling up on the side of the resonance or on the descending side of the resonance, so that you add a huge amount of amplitude modulation to your vibrato sound. And the thing about the cigar box is, of course, it doesn't have much of a sound, but it's uneven enough so that you get a little bit better vibrato. I'll just remind you what this one sounds like. I'll just play. Now the long notes are all vibrated. Okay. Now listen to the poor cigar box. It doesn't have a big sound at all. I think you might have noticed with that example, but it'll be much more so, of course, with the good violins. And so I'll give you, we have data for a large number of violins, and I picked out some for comparison. These are two Strads which were made 20 years apart. And it's very interesting to see how Strad developed in 20 years. Now, if you look at the frequency response, you can tell, and with a little bit of practice, you can tell certain features, and you can imagine a little bit what difference they will make. But I'll just let it speak for itself. That's the older one. Okay, and here's what 20 years has taught him. Okay, well, if you want to analyze this frequency response and try to figure out the fact that the beginning chord is so much stronger is this section here, up to a kilohertz, which is fatter, quite a bit fatter than in the old one. And there's also, there is not this sharp dip which the old one had. He somehow has learned how to fill in the dip with other modes. It's much, much stronger in the 5,000 to 6,000, but weaker above that, 7,000 to 9,000. So every conclusion here has to be tentative, but you know, you don't find out anything by looking at just two violins. But there's some suspicion here that above 7K, above 7,000, it's really not that important. And I can tell you that I find that point of view very pleasant, because I can't hear anything over 6K. Now, here are some new violins, and we're talking about this in the workshop yesterday quite a bit. It is now, I think it should be generally accepted that the whole idea that the Cremona violins made in the 17th century or 17th and early 18th century represent the pinnacle of violin making, and no one has ever equaled that. It's just not true. So it's as simple as that. It just isn't true. The details of this study that, the groundbreaking study that made that very clear, I don't have time to talk about, and then in any case, I wasn't involved in it other than as a kibitzer, but it's true. So new violins too can be excellent, and here are two which I've only identified with a number. I don't want to reveal. I mean, it just wouldn't be right to advertise a maker who's still working. Okay, and now if you listen to the 12, it's not obviously, to my ear, either better or worse, but rather different. Okay, and here is the worst and the best in my collection. Judging both by the sound, primarily, of course, by the sound, but you can see in the frequency response what the difference is. As a matter of fact, in this particular case, the one that I present as the worst is also a new one, and I compare it with the Vieux Temps, which is the one I played in the beginning, which I think is the best of the bunch. Now, I want to explain, there's a reason why I want to show you the worst and the best. And the reason is not just to make fun of the one that isn't any good, or just because, you know, the media are always interested in extremes, and but I'm not particularly interested in extremes for its own sake. But there is a good reason for it, and that is that I've talked to a lot of people, I'm sure you have too, who will say, you know, I just don't have the ear to tell a good violin from a bad violin. They all sound the same to me. I'm sorry, I know it's a shortcoming, but to my mind, a cheapo violin is as good as $18 million. And I always, you know, I hear that periodically. People say that about pianos too. I can't really tell a good piano from a poor piano. The sad thing is that they then buy a lousy piano for their kid who's just starting to play, and it's no wonder that he doesn't want to keep practicing, because the music that that instrument makes is so poor. But what I always ask of these people who say, I can't tell the difference, I say, have you ever tried? Have you ever had the two instruments side by side and listened to them? Because it's impossible not to be able to tell the difference. What's special about experienced people like violin makers or soloists or dealers, they have a memory of the violins they've heard in the past. And so they can make the comparison even when both instruments aren't in front of them. That is true. But to say that there's really no difference in sound is really a perversion. Now tell me you can't tell the difference between Well, research is never finished. That's a commonplace. One always there's really no end to a research project. You can't say, I'm now finished with this. You can say, I'm now going to write a paper about it. Or you can say, I'm going to get interested in something else. But you can't ever claim that you've finished a research project. And the simile I have used with my students very often is that a research project is like walking toward the horizon, and you never get any closer. In order to find out what your research has yielded, you have to turn around and look behind you and see how far you've come. And if you're fortunate and the work has done well, you've come a long way. But you're not at your destination because there is no destination, because as you move ahead, more of the landscape is revealed. And so you formulate new questions. And then when a student comes and says, I want to do a research project, what should I work on? You can tell them one of 25 things which you now see ahead of you, so the student will then start walking toward the horizon too. And when he finishes his dissertation, he can turn around and see how far he has come. So that's axiomatic for me. So I won't say we're finished with anything, but there are two particular items, smaller areas that we're working on that I want to tell you something about, just to give you the flavor of the fact that the research is continuing. And the two are the effective bow angle and the matter of directivity, and I'll explain in a minute. Okay, the effective bow angle. Now, what I mean by bow angle, by the way, is the thing that's different if you bow the G string and the E string. That the angle at which the bow is moving is the angle that's being discussed here. If you bow a double stop on the D and A strings, as you might if you're tuning up the violin, I don't know what other people have done, but I've arbitrarily called that zero angle, and then there are angles in one direction and the other direction. And the reason that is interesting is that the impulse response in a direction, well, let me start the sentence again. The way we've taken the impulse response by hitting the bridge sideways, what we've imitated then is the zero angle. That is a force that's horizontal relative to the plane of the violin. But if you get an impulse response in some other direction, like for example in the vertical direction, you'll get a different impulse response. Now, when you, it's not different in some ways, and it is different in other ways. It is not different in that after you do a Fourier transform and get the location of the normal modes in frequency, you will see the same normal modes wherever you excite it, because those are the ways the system can vibrate. A system to a physicist, a violin to a physicist is a collection of normal modes. That's what it's made of. To somebody who's trying to analyze it. But the difference is that if you hit it in one place, some modes may jump up because their natural vibration is vertical, let's say. I'm oversimplifying things a little bit. There are other modes whose important vibration is horizontal, and those will be emphasized in the other one. So without going into detail about that, it makes sense that the timbre of a real violin is different on the different strings. And I have to hasten to add, of course, nobody doubts that, but a lot of people think that the main importance, the main reason for being different is the strings. It's a heavier, the G string's a heavier string. And it is more resistant to bending, for example, than the E string, which is a very thin wire of good steel. It's got to be good steel to hold that much tension per unit cross section. So of course it'll be different, but you could, as an experiment, string a violin with 4 G strings or 4 E strings. And of course, the notes you will produce will then be completely different. But the timbre may still be different. That's what some people have observed. There's still a different timbre. And that the popular saying, or popular among violinists, is that the G string and the E string are the soloist strings. So the question is does that have something to do with the fact that the impulse response mixes in much more of the vertical? Even in the G string and the E string, where you might say the angle is now the same, but it's not the same because it's plus or minus, so the direction of the force is not the same. But in either case, it will have a greater admixture. So we want to investigate that. And the problem is our violin is you might say a normal electric violin, or actually we have our own design, but the thing we do could be duplicated on any electric violin. We get, in fact, 2 signals, because we get a signal from each foot of the bridge. There's a piezoelectric sensor under each foot of the bridge. So we get 2 signals, and the question is, from those 2 signals, can we deduce the angle of the bow? And I don't want to go into detail about how we're doing it, but of course, what you will get a big difference in that one signal will be much larger on the G string than on the E string, and the other foot will be much larger the other way. But that will depend also on whether you're playing a down bow or an up bow. And so the question is, can we process the 2 signals which we're getting anyway in order to get a bow angle out of it? And this is a first attempt. Well, it's not the first attempt, it's maybe the 4th attempt. But it's basically a preliminary attempt. Now, what you see plotted here, the abscissa is time. And this is a few seconds worth of playing. And the shading, the gray shading, which you see sort of as a background, the gray shading is the actual signal that you get from the electric violin, which is then amplified. And so there are 2 strokes of the bow here. But the stroke is in opposite directions. It's on the same string, but in opposite directions. So the first is an up bow, actually, and the second is a down bow. And the analysis that we use has successfully given us this curve, which purports to give the angle of the bow, which is labeled here in the margin 0 to 90 degrees and to minus 90 degrees. And this was played, I believe, on the D string. So the angle is appropriate to a D string. And with a fast digital signal processor, which we're using anyway, that can be done in real time. And so that the output will be a mixed output of the two outputs that you get. It'll be mixed according to this proportion. And our hope, of course, is that that will improve, that will make the sound even better. Okay, now the second thing is the directivity of the sound, which I don't know, it certainly was mentioned in the workshop yesterday. The directivity of a violin, the sound radiation from a violin is very complex when it comes to directional dependence of where the sound goes. But for an electric instrument, any kind of electric instrument, be it an electric guitar, violin, or keyboard for that matter, they'll all have the same directionality characteristic, that of the loudspeaker through which it's played. If it comes out of a loudspeaker, it'll have the characteristics of a loudspeaker. And I quote Pierre Boulez here. This is something from 1983. Le haut-parleur anonymise la source réelle. The loudspeaker anonymizes the real source. Now, you might say there's no such word as anonymizes in English. Well, there isn't one in French either. So you don't worry about it. The meaning is clear. In other words, his point of view was that there's a real shortcoming in playing recorded music. Of any kind, whether it's from an electric instrument or from real instruments. But when you play it off a CD, the only directionality you get is the directionality of the loudspeaker. And the example I've used is that what it would sound like is if you're in one room and the violinist is in the next room and the wall doesn't let any sound through, but you've cut a hole about this big, if that's the size of your speaker. And the sound that you get in the second room is the sound that you get from a loudspeaker when a violin plays into it. Now, it's actually, it's not too bad if you're playing a trombone, for example, because most of the sound comes out of a radiator about this size, namely the bell, so that you can do reasonably well with instruments like that. But if you get to a violin, the situation is very different. So here is some data that I took. Actually, it was published in 1997. And this shows 4 violins. These are graphs taken, I'll tell you in a minute, graphs of what? Graphs taken on 4 violins, 4 very different violins, both in quality and in price and in provenance. I won't go into details because they're identified just by a 3-letter code. But there are 4 different violins. And the experiment was that you make the violin emit a sinusoidal sound. Actually, I'm simplifying the experiment a little bit, but there'll be less to explain this way, and in principle, what I'm telling you is true. You have the violin play a sinusoidal sound, a pure tone of varying frequency. You sweep it from the beginning of it. Well, on top you see the scale of notes: F3, A3, C sharp 4. If you remember the suffixes, the C4 is middle C. So that's around 260 some. And what you see on top is intervals of a major third, so you can orient yourself musically. On the bottom is the actual frequency in the logarithmic scale. Now, what is it that you measure? What you measure is the sound that's being picked up by two microphones in very different directions. That is, they're not next to each other or anything. They're more or less independent directions that, but otherwise arbitrarily chosen. And you take the ratio of those two signals, and that's what's plotted here. So it's plotted in decibels, and each one has its own 0 decibels. They're just, the drawings are shifted. So this region from low frequencies, and I don't want you to worry about this feature down below, down at the very low frequencies, which we understand, but it's not to the point here. Up to about F5. And that's, you know, about 750 hertz. There, it's essentially, the radiation is isotropic. That is, the two microphones get the same signal. They're at the same distance away, I should add. So I get the same signal, but then above 750 hertz, something very wild happens. Very wild, jagged up and down. The different violins have no correlation between where the jags come. But they do have this in common, that the frequency, the spacing of the jags is, as you get into the kilohertz range, it's less than a semitone. Which means that if you play an F and then you play an F sharp, you have a completely different, unrelated directional pattern. So, to make a speaker that actually produces that kind of detail and simulates those violins so they look correct even to a computer, even to a microphone and to a computer, or a computer can plot these things and calculate it. That would be very hard, very expensive, and I would say very useless, because I don't think the ear can distinguish exactly what the pattern is. What the ear does distinguish is that there is a richness, the kind of richness which stereo introduces, but much more so. The violin is like a lighthouse, a number of lighthouses sending out beams in various directions. And for example, when you do a vibrato, those beams move up and down, or maybe they move like that. And of course you get reflections from the room, so that what you get is an incredibly rich pattern of, including vibrato, among other things, but also, generally speaking, if you play a real violin and listen to it live, not recorded and not listened to it through a small hole in the wall, but you're actually in the presence of the symphony orchestra and the soloist, what you hear has a richness that no single speaker can imitate in detail. However, you can make speakers that imitate it qualitatively. We've done so. Well, actually, the first publication of this was 1997, but we've continued to work on that with the thought that the idea is that we want to produce a field of sufficient intensity which is sufficiently rapidly varying so that the ear, and when I say ear, I always mean ear plus brain, the human perception will be of directional tone color. This quality, I've named it directional tone color. It has different tone color in different directions. So that's also something to be worked on. And let's see, what time is it? Well, it looks like I finished on time. Okay.